Hello students, my topic of discussion is crystal field theory. So this is basically for chemistry students in their master's level. So crystal field theory is an important part of coordination chemistry. So this describes the bonding in coordination complexes. So this is a very important theory to know about them. So what is the very important here? You know, alumina crystals. So this is your alumina crystal, which is colorless, which is nothing but aluminium oxide. But when you dope it with little bit of chromium, you get a very nice pink color of this crystal, which we call it as ruby, and we use it as a gemstone. So what is the source of this attractive color? So this can be explained by crystal field theory. So it gives reason behind your color and magnetism of coordination compounds. So how coordination compounds form? In a coordination compound, metal is there in the center and ligands surrounding itself, which are negatively charged, and metal is positively charged. So what is crystal field theory? This is borrowed from solid state physics, which was originally developed to describe the electronic structure of metal ions in crystals, where they are surrounded by anions that create an electrostatic field. Now, we have transition metals which are having d orbital in itself. So this d orbital, there are 5 d orbitals are there, and their electron distribution in different direction is different. Now these are the d orbitals, 5 d orbitals you can see. But when the ligand approaches the metal, then there is repulsion between the metal orbitals and metal electrons, and the metal d orbitals and the electrons of the ligand. Now when any bond formation happens, then what happens? This is metal ion, and this is your ligand. So when they come closer, there is attractive force, because they are two differently charged. One is positively charged, another is negatively charged. That's why they have electrostatic attraction between them. And whenever there is attraction, you have to remember that energy will decrease. And whenever there is repulsive force between any two things, the energy will increase. Now, in a equilibrium situation, when in energy is minimum, that is your bonding situation when metal and ligand bond forms. Now, when there is d electron, as d electrons are spreaded in the different shape, have different shape, therefore their interaction with the ligand orbital is also different. Let us see one YouTube video which will more clarify your concepts.
Octahedral splitting. Isolated metal with 5 degenerate d orbitals. That is dxy, dyz, dzx, dx square minus y square, and dz square. 6 ligands approach the d orbitals along the x, y, and z axes from both the sides. As the ligand approach along the axis, as the dx square minus y square and dz square orbitals are spread along the axis, experience more repulsions, acquire high energy. These orbitals are called dGe orbitals. As the dxy, dyz, dzx orbitals are spread in between the axes, experience less repulsions due to interaction with ligands, and hence have less energy. These are T2 orbitals.
So you have seen how this d orbitals split due to their different shape and spreading in different direction. And due to the splitting of d orbitals, electron from lower level. Now we can see how this splitting of d orbital is occurring, and due to this splitting, this electron from lower level, when it goes to the higher level, it absorbs energy, and when again from higher level it is going to the lower level, it can re-emit the energy in the visible region. If the energy in the visible region, then you can see the color of the compound. So now I think you can understand how this color of the ruby is appearing by just doping this colorless alumina with the transition metals like chromium. So thank you for your attention.